Hey guys, thanks for watching part 2 of assembling your city. This time it's layout generation. We're not going to go over all the details there are, we're going to do some of the final layout generation in one of the upcoming tutorials, but for now this is the basics you can use to start doing some layout generation. Alright, let's dive in. Alright, as usual, we're going to place down a geometry node and let's dive in. First of all, I want to have some test geometry. So just like the last part, we're going to place down a curve, then enter the top view, and let's draw something that could be our building. And for this it's just important that you kind of try to get the right angles, because we are going to try to work in a grid or something like that. Doesn't need to be a perfect grid or something. So let me just remove a few points, and yeah, it can be something like this. Something we like. Alright, and let's close this. Then enter perspective again by pressing 1. And now place down a transform node. In the transform node, the scale in the y direction we're going to set to 0. And then I want to place a sort node, just as some cleanup. And set it to sort by vertex order. Then place down a convert line. And after the convert line, we're going to place down a rest node. This rest node is mainly important for in the end. But right now, we're going to make sure that all the corners are at an exact right angle, because that will make the process in the future a little bit easier. To do this, I'm going to place down a for loop. And what we're going to do is select each primitive and make it straight. But you cannot do this all at the same time, because then at one place, if we were doing it with each primitive at the same time, each point will be done at the same time, which means each point gets 2 values, which would mean the corners wouldn't be straight. And that's why we're going to do them one by one. So for that we need a for loop. And I want to have a import node. And we're going to place down a primitive fob, and we're going to set this primitive fob to be a detail fob. So let's set it to detail, and let's also call it a detail fob. There we go. And well, you could do this in vex or fobs. I'm going to show you a few things I like in fobs, but I would have probably done this as in vex if I would have wanted to make it a little bit more of a finalized system. Alright, let's dive into the detail fob. And let's remove this node over here. And then the first thing I want to do is import detail attribute. And what we're going to be importing is from the second input. And because we have the meta node, we have it wired into the second input. And that means that right now we can get the iteration value. This is a detail attribute, and it will give the current iteration number of the for loop. Which is nice, because if we look at our point number and our primitive number, everything is ordered nicely, which means that if we are at primitive number 0, then we are at the second point of this primitive. Same for 1, same for 2, and that's a nice little thing, a little trick we can use later on. But for now, we're just going to get the iteration value, which is an integer, and I want to use this with an inline node. So the inline code node, so inline code. This is a neat little trick if you want to swap a little bit between vex and fobs whenever you find it's handy to do the one thing in fobs, because you can iterate a lot, or if you really want to have the fast, powerful stuff that the vex always have, then you can use, you can write it in here. Alright, so this iteration number is right now our primitive number. In this result, we're going to wire it in, and then I want our input 1 to be the second input. And we're going to have one output, and that is an array of integer numbers, because we're going to get the prim points of this primitive. So we're going to set it to integer array, and then we're going to type in $prim points. So that's going to be this output, so I'm going to call this print points and also label it print points. There we go. And that's this value, that's this variable, and this is going to be equal to the function print points, $geo, and then $prim num. And let's close it. Alright, now we need to label our inputs, and the result from our iteration one is the prim num. Oh. And the result from our input is geo. And the cool thing is, right now this is a nice preset that will give us, well, the print points belonging to a primitive. And right now we can save this as a well, as its own preset by just pressing save preset. You can do it over here, give it your own name. I'm going to call it new preset, save preset, and of course you need to select where you want to save it, and saved. So now I can select this new preset to automatically get this little line of code, which is a nice thing to have. Then I'm going to place down a get array element, because we always have 2 points and they're always, well, 0 and 1. It doesn't matter the order we're getting them in right now. So we can get element 1, and we can get the second index. There we go. So we have the first and second point of each primitive. Now we need to get their positions. So place down a get attribute node, wire in our point numbers, and let's get the position. First input vector. Alright. And also do it for the second point. After that, I want to place down a vector to float. So we can select the X or Z direction, or X or Z value. And now what we want to do, if you look at this real closely, I want to align this primitive, which is horizontal. I want to align those 2 points in their X direction. Because right now this is the X direction, so I want to align those in the X direction. But for this one, which has a vertical alignment, we want to align the points horizontally. So that's what we're going to be doing. First, place down a distance, and what we're going to check is the distance between the difference in the X value and the difference in the Z value. And depending on which one is larger, we're gonna set a switch. So let's compare these two. And right now, set it to less than. All right. So this is our basic switch value. After this, we're gonna mix some values. So this is basically a lerp. And in this lerp, we're gonna throw in the 2 X coordinates, the 2 X values, and the 2 Z values, both only going into their own thing. Oh, this needs to go. All right, that's over there. Let's remove these 2, and let's get the Z values in there. All right. Now, after this, we're gonna pair our switches. So let's have a float to vector 3, which is over there. And in here, we're going to wire in the original X and the adjusted Z, and vice versa. And we're going to do this both for both points. So first, let's wire in the original X value, and then get the mixed Z value. And this one needs to be that thing in reversed. So it's going to have the mixed X value and the original Z value of our top one. And then the second one is going to have the mixed version is going to be the same, but the original point value needs to be from the second point. So let's wire those in. There we go. Then let's place down a switch node. This switch node needs this value to determine which values are going to be used. And let's wire those two in. There we go. And then a set attribute. We're going to set the position of the points because we're going to change their position. And for those of you who don't know that yet, if you press Alt, you can get these little bubbles, which help you to make a nice and clean system. So there we go. Let's copy this one. Second value, and this one needs the second point value. There we go. If you look at this, we of course need to wire it in first, otherwise it won't work at all. And there we go. And this is less than, so there we are. Now we have some nice straight angles going on. And to make sure this is as fast as possible, right now it's a very small thing, but just to see how we can put this into a compiled loop, let's place down a null node. And this null node is going to contain the amount of prims, so n prims, because we only need to loop it once per prim, and then it's all done. And we could make it do random prims first, but it doesn't really matter that much. So let's take this value and type in n prims. Let's reference our null node, which is also called n prims. And there we go. But this won't work yet in a compiled loop because we need a spare input. So let's add a spare input, and then this line we're gonna do Ctrl X and place -1 here. And then over here I'm gonna paste it and remove those two to make sure it still works. Voila, it still works. And then we can place down a compiled block. And this compiled block is going to encapsulate this whole thing. We can make sure that it's set to multi-thread when compiled. And there we go. Now it's multi-threaded in a compiled block. Nice. Next up, we're going to place a add node. And this add node is going to make this primitive hole again. So let's delete geometry, but keep the points. By group and closed. And now we have a nice primitive again, which is hole. Then I want to place a fuse, because we're gonna place all these points onto a grid. So let's set this to grid, and let's add a null node. And this null node is going to have the grid size. So let's call this grid size. So there we go. And let's set it to something like this. Let's copy this into the fuse. And the first one we don't need it, or the second one we don't need it, because we don't have any stuff going on in the Y direction. So let's delete channel to 1. And over here, let's make it a little bit smaller. There we go. So now it's nicely in a grid, and that is going to help us a lot, especially in the future. So first what we want to do, we want to make a grid which is exactly this shape and also has the exact same subdivisions. So let's place down a grid. And what this grid is going to need are some values, and those values we'll get from this null node. And first of all, we need the bounding box, and second of all, we need the centroid. So we can do this by dragging in two O3 vectors. And the first one I will be calling bounding box, and the second one I will be calling the centroid. There we go. And to get the bounding box, we can have this bounding box expression, which will be referring to itself. So we can do like this. And then we want to have the size for the x direction, so x size. There we go. If you look up Houdini expressions, then you can find this whole list of expressions and how to use them, and also it usually says it when you start typing it. So that's actually pretty easy. So let's copy this one into the one on the side and the one on the right, and let's change those values to y and to z. we're going to do the same thing for the centroid. So let's type in centroid. We're going to select ourselves. There we go. And we are going to select the X direction. There we go. Now we have the centroid for the X direction. Let's copy this into the second and third channel and change those to Y and Z. There we go. So these are some very helpful expressions. So also right now we would just tell you to save this preset. And let's save this preset as bounding box info. There we go. So if you would now be placing a null node, you can select it and select the preset bounding box info. And if you install the qlib library, so this is a very awesome thing. So this is a very awesome thing which has just a lot of stuff for you, where you can get a lot of different information, also bounding box info, everything you want, just with a click on the button, and of course a whole lot of nodes. Alright, we won't be using it for now because this is a simple tutorial. And this is the information our grid is going to need. So at first, for the grid size, we can select the X direction, do copy parameter and paste it in there. Do the same for the Z direction, paste it in there. There we go. So now it's still a little bit offset, and that's why we need the centroid. So let's copy the centroid and place it in there. And now if we make this gray and we look at this thing, it's already quite far, but it's not completely done yet. Because we need this grid to also follow our grid size from the views exactly. And to do this, we can just simply first select our channel over here, size, copy parameter, and X is going into the columns, and our Y is going into the rows. There we go. And now we're going to divide this by our grid size. Paste it in there, do the same for this one. And you'll see that it's now almost perfect, but we need one more thing, and that's to add one number over here. Because we have more rows than actual segments. One more, and to be exact. There we go. So now we have a nice grid which perfectly encapsulates our primitive. And what we can do right now, if we want our original primitive to have this as subdivisions, is use the Voronoi fracture node. So let's get this Voronoi fracture. And we're going to wire in our primitive on the left. And the points we're going to wire into are not this grid, but are going to be the centroids of those primitives. So if I would be placing a point loop or vex or whatever, you can select point, you can do the add point function, and go over there and remove prim. Let's remove the original primitive. There we go. Oh, this is set to points. Oops, it needs to be set to prims, of course. There we go. Let's call this prim to centroid. Alright, and this is going to be wired into the Voronoi fracture, which means right now we have subdivided our original polygon and we don't need an interior, so we can remove that. And now we have nice squares. You might think to do this with the polybricker node, but the moment you get these basic perfect corners and then it needs to continue, then it misses some subdivisions in some places. It's way less consistent and also kind of heavy. So I usually like to use the Voronoi fracture because it also helps with getting the rest position as perfect as it is right now. And if we can have a look at that. So let's place down the point wrangle. We're going to look at our initial rest position. So at B equals at rest and close it. There we go. As you can see, it's not working perfectly yet. So that was the rest position we were getting from this node over here. But it's not working perfectly yet. And that's because it's subdividing it into squares, but it's subdividing this large polygon and it doesn't know where to get the value from exactly at this moment. So we first need to divide this one up into smaller segments with a divide node, and we're going to divide it up into triangles, and we're going to avoid small angles, so we have a nice distribution of triangles. Now, if we do it right now, you can see we have no distortion regarding weird clipping polygons. And if we look at our original rest position, so the original shape of our building, you can see where the deformation is happening. We can later on attribute blur this maybe if we don't really like these bendy lines, or well, whatever you want to do. But for now, I think this is fine. The only thing I don't like are these, well, the remainders of our divide node. So we're going to be removing them. First, place down a group node, and with this group node, we can set it to edges, and we can select it to include by edges, and then do something like unshared edges. Because right now, and of course, don't select everything. And because we are selecting all the unshared edges, after the Voronoi fraction node, every polygon it fractured into is its own polygon. It's not connected to the other ones. So that's why you see this grid as being the selected group. These original lines were used for the subdivision, but we don't need them anymore, and we're also not selecting them because they are not cutting up the polygon and really screwing up the connectivity. That's why we can select them. So right now we can place down a dissolve node, and with this dissolve node we can remove those points. So that's, we have a lot of pieces. We can with group 1, so we can select group 1. Don't remove inline nodes. Alright, and delete non-selected, and there we go. So now we have some nice squares, which is what we wanted. Then place down a fuse node, because we do want them to be connected, not to be separate entities. And after that, a convert line. So we are heading towards the inside of the building layout generation. So for now, we're just gonna make the main frame where what we're gonna use in the upfollowing tutorials to generate the layout. So this is, I'm gonna show you some tricks to get certain patterns inside of the building layout generation, but yeah, there are just so many different layouts. You really need to know exactly what kind of building you're making before you can generate its layout. So that's what we'll be focusing on in the upcoming tutorials. So we have this grid, this raster of lines, and what we want to do with this, well, first we need to know where there's a door. So I'm gonna place down a group. You could do some fancy door selecting by using well, a sphere you can place somewhere and it will select the closest points or anything. But for now, I'm just going to do it simple, and I'm going to be selecting the point I want to be the door, and I want point 54 to be my door. So I'm going to call this door point. I'm going to be selecting a point, and it's going to be 54. There we go. And now I have my door selected. Then I'm going to place down a sort node. And this sort node is gonna jumble up all the points. And then with a group range, I'm going to select some random endpoint. So set it to points, and let's select 1 out of 8. And there we go. We have some random points. Then after this, we can place down a find shortest path. And this find shortest path node is a really cool one. So the start point is going to be the door, and the end point is going to be group 1, or well, let's call this endpoint. So the endpoint is going to be endpoints. There we go. And from each end, so any start to each end, that's what I want. Now we have a very basic layout for the walkways within the building. And this looks obviously very weird. Although I would recommend you to just go through some building layouts of actual buildings, and you can sometimes see some really seemingly weird generated patterns. But for now, this is just a cool trick to use an explanation on how to use the find shortest path node. But we can adjust this a little bit. So first of all, let's introduce you to how to use noise to change this. So we have primitive up. We can insert this primitive up over here, and in here we are going to also let's visualize it over here, and let's place a noise node, this time the anti-aliased flow noise, and we're going to wire this into the color. There you go. Then also let's go to Vex options and curate input parameters so we can adjust the noise from up here. Let's have some higher value for the amplitude, and also let's place down a clamp. And this clamp is just to make sure we don't have any negative values. And this is going to be our cost attribute. And this cost attribute I will be calling a bind export node prim cost. There we go. And now in our find shortest path node, we can go to path cost and we can say, okay, this primitive, if it has this attribute, so prim cost, that was the correct one, right? Quick look, yes, there it is. And right now it will look at this value and use it to calculate the shortest path. So if this is a very high number, it will try to avoid those primitives. And if we now look at this, it already looks a little bit different. And we can play with this noise to get a certain look we like, a certain pattern it will start generating for random buildings, if you will be generating a lot of random buildings. So that's mainly just a cool trick. But usually your building has some kind of structure, some kind of hallways, which are kind of the foundation of your building. And I'm gonna give you an example on how to create those. So after this convert line, we're gonna drag this stuff down a little bit, and I will be placing down a primitive up. And inside of this primitive up, I will be getting the position. I will place down a vector to float, wire that into the position, and now I'm going to use the x value to create a sort of ID attribute. And to do this, I will multiply it because there are some inaccuracies within Houdini, as always. Well, because this is very sensitive to very slight changes. So I'm going to round it down to a few decimals. And to do that, I'm going to place down a multiply. And then I'm going to be placing down a round to integer. And then a divide node. Then I will place down a constant. And we'll set it to 1000 or something. There we go, wired in both of them. And then with a bind export, I will be able to call this prim ID. There we go. And now if we would be placing down an add node and a sort node, first wire in the add node, and let's remove geometry with key points and do it by group and do it by attribute, and the attribute is prim ID, or wait, what was it? Yes, it was prim ID, which is supposed to be a point attribute, so this needs to be a point value. Luckily we can just simply change this to be a point value. There we go. We have some straight lines shooting downwards, and these straight lines are based on, well, the points we have over here. But as you can see, we have some random points in there, and we can remove those with this dissolve node by removing inline points. There we go. And next up, we need to place down a sort node. So this is the Z direction, so I will be sorting them into the Z direction. And to make sure this works properly, we need to disable this point wrangle, because this is placing it down to the original point, and right now I want it to be at the exact same X and Z position. So there we go. we have some straight lines. And now imagine you want to delete 1 and 2, so let's place down a group range. And this group range is going to select primitives 1 out of 2. There we go. And then let's just blast it. So let's call this group delete me. And let's delete that group with the blast. There we go. And we could do this in both directions. So let's copy this over there. So this is just an example of how you could create a certain structure in your building. You could do this in all sorts of ways. But for now, it's a nice little example. So let's use the z value this time, and this sort needs to sort by x in that instance. All right, let's merge these two together. Then place down a fuse. Give them their own cost value. So a point wrangle. Let's place it down, or this also needs to be a primitive wrangle. There we go. And let's refer this to channel F. There we go. We're going to be setting the prim cost attribute. So f at prim cost equals this. All right. And now we have a nice channel to set this attribute. And if we go into our geometry spreadsheet, so new paint tab and geometry spreadsheet, you can see our primitives have a prim cost. And now if we would be merging this with our original mesh, so right now we've selected the endpoint, so that's nice. And here we're setting the noise. So then place down a merge and wire the two of these in there. Place down a fuse node. And we can throw it into the find shortest path node. Let's make sure that our adjusted prims are on the left. And then I want to have this grouping to be done actually after this. So the noise can be done in the beginning, and this grouping can be done over there. And there we go. So now we have some noises to play with, and we also have another value we can play with, and that those are these lines. So we can get a little bit more of a structured form. And if we look at this curve in the beginning right now, it doesn't have the right shape yet. So before the shortest path, we are going to wire in our rest point wrangle. So there we go. And now it follows it correctly, but there's only one mistake over here. Like over here, there shouldn't be a line. And you can see that's happening over here. And a way to remove that line is because we know each segment has well, right now we don't really have a segment, so let's first place down a convert line. That was one node I forgot. So between the fuse and the primitive wrangle, let's place down a convert line. And then if we place down a measure node and wire that over there, and we're gonna set it to perimeter, and then a delete node. And the delete node is going to delete everything which is too long. So let's set it to expression. And let's delete everything from the perimeter, which is longer than, and that is depending on our null node over here. So let's copy this value. Let's copy this in there. And let's multiply it by 1.5. So it's always in between 1 and 2 sizes of itself. And there we go. So here you can see we've deleted that primitive. And now we don't have any primitives anymore which go into the wrong direction. So this was the basis of this layout generation tutorial. And then next up we will following up some more designs we can make with this. But yeah, this is the basic, so have fun with it and thanks for watching.